you've been looking for a live audio spectrogram tutorial built with OpenGL and Python, it goes for like 2.5 hours, then you've come to the right place. This is what we're going to build. What's on the screen right now. This is a live audio spectrogram. It is taking an audio signal from my microphone as I'm speaking into it right now, and it's showing you the audio wave in green, and it's also giving you a breakdown of the frequencies that are present as I'm speaking in the signal that's coming from my voice. It uses the fast Fourier transform, and it can be used for lots of different things. It can be used for decoding audio signals and turning them into an image and passing them into a convolutional neural network, if that's your thing. Or it can be used for just its aesthetically pleasing properties, which is what I've been, raving about for a little while now. So if you want to learn how to build this, then, follow along and let's get to it. Okay, first thing we're going to do is set up our project. So pick a location wherever you want to work from. It's fine. I'm going to be working from YouTube/Spectrogram. So I'm going to make dir Spectrogram, seed into that folder, and this is where this is where everything's going to happen. So first thing I'm going to do is create a virtual environment. I'm going to use virtual env, which on Linux, if you don't have it, you can just run sudo apt install Python 3 virtual env. And I've already got it, so yes, no problem. And then I'm just going to run virtual env. And then I'm going to call it venv for virtual env. And you can see it created this folder here, and it contains everything inside it. We don't care what's inside, like we can just ignore it. We don't need to know the details of what's inside. And that's going to contain all of our Python packages. So the next thing we're gonna create a make file. So just touch that. We're going to make a folder called app, and we're going to create a single file in there for now called window.py. Now if I run tree, you can see my version of tree hides our venv, so that's why I don't see it, but this is what our project should look like for now. Now, as I said, I'm going to work in NeoVim, but you can work in VS Code just as easily. So, if you work in VS Code, if you've got that installed, just go code dot, and that will open. Yep, that will open this, and you can see I've got the window make file. You can work in here if you want, or in the terminal. I prefer the terminal, so I'm going to do that, but you can do everything you need to do in VS Code. That's fine. So as I said, I'm going to use NeoVim. First thing I'm going to do is open our make file, and I'm going to create a make routine or a target that's going to run our window file all by itself, nothing else. So I'm just going to create that window, and then I'm going to source our venv, and then in the same line, or with that sort of activated context, I'm going to go Python app window.py. That's all I'm going to do. No need to do anything else for the time being anyway. I'm going to open the window file as well. Actually, first we need to install our packages. Silly me. So I'm going to source venv bin activate, and there's 2 packages we need to install. And we can just go pip install pyqt5 and ModernGL and install those. So pyqt5 is a Python wrapper for Qt, which is a cross-platform windowing system. which is right here. This is the homepage of the documentation for Qt. Very, very, awesome GUI framework. And ModernGL here is an implementation of OpenGL for Python, which is very, very useful. It's wrapped up very, very nicely. It allows us to create things very, very simply. And we're going to use these two packages together. And this is a pattern that I use all the time, and I'll show you how it's done, basically, or how I go about it. So we need to import ModernGL and some things from the PyQt framework. QSurface format is going to allow us to set our some OpenGL configuration. We need to inform Qt about how to do that. Class called window, and we're going to subclass the QOpenGL widget object. We're going to define a frame rate. I'm going to call it 61. Now, what we want is we want it to be 60 frames per second, but the way that the timer works that comes with Qt, it doesn't allow us to set strictly 60 frames per second, because you have to set it in whole number milliseconds, and there's no way to give 1/60th of a second in milliseconds without using a floating point number. And so what we do, the reason that I add 61 is because we make it a little bit more, and OpenGL limits it at 60 frames per second. And so it that's why I pick such an odd number. You call super init to make sure that everything QOpenGL widget is initialized. And we're going to set some surface format configuration. A lot of this stuff doesn't really need a lot of explanation, but it is required for. We're going to allow multi-sampling, which is going to improve the quality of what's drawn from our OpenGL window. We're also going to set a shortcut that's going to allow us to close the window with a very simple hitting the escape key. That's why we imported the Q shortcut. It's really easy to add something like this. You just go T, we need the key. And then we want to call self.quit, which is a function that we're going to create in a second. Close. And there's another function we're going to create. We're going to create a class method. And it's just going to allow us to initialize our window very, very easily by just calling a window.run. So I'm going to call it run. We're going to need to pass the class there. So all this is pretty much boilerplate while we just figure out when we just get our window up. So our main window will be the class that we passed in, and we'll just go main.show. And then we need to put our app in an event loop. And that should be all we need to just get the window up and running. There's a lot more we need to add, but we'll get to that in a second. So we're going to create a function that we only want to run when this particular file is run, because we want to be able to import our window and use it elsewhere. So I'm just going to call it name. This is a very common Python pattern. I'm sure you've seen it before. Window.run. That's why we created this class method. So it's super easy for us to do that. We save that and then Control Z to come back to the terminal, but we can hit FG, foreground, to jump back. I'm not sure if you're familiar with moving around the Linux terminal really easily, but that is very useful. It's locked into my memory. I use it all the time. And then because we created this window target, now we can just run make, and it should open our window for us. Okay, first problem. It's not Q widgets, it's Qt widgets. So silly. I knew there was going to be there's going to be a lot of typos, because that's just how I roll. Okay, now try again, make. There we go. Now we've got a, black, you can't really see it. It's hard to see, but that's our window. It's up and running. Sweet. Now, there's a few things we want to add to this window. We're going to fix the size so that we can resize it. We don't want to be able to resize it for this project, for reasons we'll get into later. It's just a lot easier, because then we've got to make it responsive and sort of outside the scope of that. So we're just going to fix the size of the window, and we're going to set up an OpenGL context so that we can start drawing. And the first thing we're going to fill in is just the background. So we're going to give it a solid color background. So we come back here, and inside there's a few functions, there's a few methods that we can override here in this Q OpenGL widget object class, and they are, just make a section here, and we'll just call it OpenGL, OpenGL logic. It's going to be def initialize GL. These are going to get called for us. We won't be calling them ourselves. Resize GL. And it gives us our width and our height of our window, so we can readjust our elements inside our window accordingly, or as appropriate. And the next one is paint GL. Now this is called when we want to render every frame render, when we want to actually do our OpenGL, like draw what we need. It activates our OpenGL context, so that when we call OpenGL render this, draw this, blah blah blah, it's going to render it to the screen. It's gonna set everything up for us to do it. If you've never done graphics programming before or anything like that, this is a really easy way of just setting everything up, and you don't need to worry too much about any of that stuff. And we're going to set up an OpenGL context first. So we're going to go self.ctx for context, and then ModernGL create context. This is why we're using these two things together. You don't have to use ModernGL. You can do OpenGL a much longer way, but ModernGL just makes it so easy that we're going to use it. I would almost not even consider using normal straight OpenGL anymore. It's just so good to use something like ModernGL. And you don't have to use Qt windows with ModernGL. You can use, there's a whole list of, you can use like Tinker, I forgot the names, SDL, I'm pretty sure you can use pretty much any like windowing system that creates an OpenGL context. You can use ModernGL with it, and ModernGL documentation has a lot of documentation. I can find it quickly, otherwise I won't bother. Not sure, but yeah, it's really good. Trust me. We'll see that as we build out our project. I'm going to set a clear color which is just going to be a flat a green. Let's give it something that's greenish. 4, something like that. Give it 5. We're going to enable multi-sampling, which is multi-sample, which is just something that improves the quality of it. And that's all we need there. And our size, we're going to set our Windows size. We're going to need a fixed size. So we go self dot set fixed size. So we're going to call it 1280 by 720. This gives us a 16 by 9 window. So save that. We've got our flat color. That should work. So we'll come back here and we'll go make. Go make, and there we go. There's our window. It's fixed, very, very small. There's one problem with that is I'm working on a 4K monitor, and so my 16 by 9, my 1280 by 720 should be about twice the size because I'm working on a 4K monitor and I've increased the scale by twice. It's annoying, but basically I want to render this slightly differently. So I want this to scale with my Ubuntu scaling factor, which I'll just show you quickly. If I go settings, see how I've got this 200% on my, if I go to my screen display, display 1, display 2, both of them are at 200%, which means that they are stretched, like they're scaled upwards so that they're much bigger. So what I want to do is I want to add an attribute. I want to add an attribute to Qt to tell the window to respect my system's scaling. You might not need to do this, but this is something that I'm going to do on my machine, and you can comment it out or leave it out depending on what, you know, if you have a scaled up, people have different systems, you know what I mean? So if you want to scale it up to respect your, you know, if you have some sort of extra scaling, then you can. If not, you can just comment it out. It's totally fine, but it's something that I, you know, kind of need, or something I like to add because, you know, I like all of my windows to be, you know, to respect the scaling of the settings. So in our run method, it's just going to go right here, and it is Q application dot set attribute and that should be it. Go out here, save, clear that again, and there we go. Now it's twice the size, so it's respecting my system's scaling factor, which is, you know, as I said, maybe you need that, maybe you don't need that, but I thought it was important to show that. So now we're good. Now we've got our window working and we can move on. Okay, so what we want to do now is we want to add a few interface methods to our window class. So we're going to open up our app.window, and down here we're going to add a section. We call it interface, and we're going to define some functions here that are going to be called when we subclass our window. So this window class is something we're going to subclass this later, and we're going to build our app from that. And there's a few functions that we want to be called automatically when certain things happen, and we'll go through those now. So the first one is going to be init, and we'll just pass for now. The next is going to be size. And this is going to be called when the window resizes, and we can do any OpenGL related, updating our projection matrices, things like that. We also need a draw call. So this is going to be called whenever we want to actually paint or render to the screen. And this is going to receive a DT, which is the difference in time from the current frame to the last frame. So it's going to tell us, so if it's 60 frames per second, it's going to be 1/60th of a second. And we're going to have one more, which is going to be exit. And this is going to be where we can do any sort of cleanup. And that's going to be useful if we need to release resources or anything like that. And actually, instead of pass, we're just going to print what's happening. So I'm going to print init, print our size with the width and the height, print draw with the DT, and also just print exit. Now, we need to call these functions from somewhere because they're not being called as of yet. So the first one is going to be really easy. It's going to be called from inside this initialize GL. Now, why didn't we put it in here in our underscore or our init file? Like, why didn't we put it there? It's because when that init is called, it doesn't have the OpenGL context activated. And this is something that is, necessary if you're going to, call OpenGL functions. You need that context activated. If you don't have a context, it's just not going to work. This is why we're using Qt and this OpenGL widget here, because it does all this stuff for us. It's really, 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 really handy. So we're going to call from in here self.init. That's all. Inside resize, this is where we're going to call self.size, and then we're just going to pass that width and height, and that's pretty easy. Now, the reason why we didn't call it resize is because Qt already, these widgets already have a self.resize function that we can't just override because it's integral part of how it works. So we don't want to mess with that. Inside paint, we're just going to call DT, and we'll call it just one, and then we're going to go self.draw, draw not paint, and we're going to pass it DT. We'll get to that in a second. And then on our quit, we're going to go self.exit first before we call close. So we give it a chance to do some cleanup. Now our DT is going to be really simple. We need to import the time. I've got it right here. I think I import time. And then we're going to just get the current time. It's going to be now equals time.time. And then we're going to compute our DT. It's going to be now minus self.t, which is something that we'll set. Now this self.t, we need to make sure that that exists. So we're going to come up here, just above our shortcut, we're going to self.t equals none. And that's all we need for now. And that should be it. So now when all of these four key actions, these four key events, whenever they happen, we're going to get our interface methods are going to be called here. So that should work now. And we're just going to go make window. And it opened, and then we can close it. And we can see what's happening. So we've got our init that's being called. The size is being updated. We're being notified of the size of our window, so we can do whatever we need to do in our OpenGL projection matrices, etc. We've got two draw calls. So render is being called twice. It should be called continuously, but we've got to set up a timer for that. We'll do that in a second. And then on our exit is being called before the program finally cleans up. So this is exactly what we want. This is great. So we will add a timer now so that this draw is drawing continuously. So to do that, we're going to come up here. We already imported our Q timer up here. So we already did that at the very beginning. And we're just going to create a timer. Self.timer equals Q timer. Update is a function that is contained within the this Qt object, and whenever we call update, it's going to automatically call and activate our PaintGL down here for us with the OpenGL context and initialize, all that sort of stuff. So all we need to do is call self.update like this, and then we need to start our timer. And that should be it. So when we save that and then we rerun our make window, we should get the draw being called continuously, if we spell things correctly. So this should be Q capital T. Try again. And make window. And there we go. See, it's humming, you know, it's being drawn at what we can see here as at about once every 1/60th of a second. And that's great. That's what we want. And now we're going to update this print. So instead of just using print functions here, instead of just printing things out like this, we're going to create our own logger, which is a much better way of logging out information. So to do that, we're going to close our window file. And if we go back tree and we just look at our structure again, what we're going to do is going to create a new folder inside our app utils. We're just going to call it utils. That's all. To create a new file. And we're just going to very quickly make our logger, a custom logger. And there we go. And we'll just add a section here as well, because we might add some additional things to our utils function in the future. Cool, save that. And make sure we don't have any spelling errors. Looks pretty good. And now we're going to open up our app window file again. And we're going to import our logger. So we go from utils, import logger. And we created a custom logger like this so that we can, when we set our level and when we set properties on our logger, we could have our logger printing in like 100 different places, potentially. And we want to be able to flick on and off functionality for that logger in one hit. So instead we're going to replace all of these print statements with our logger.info, because it's just information that we want. Replace all these. One small issue, we can't add arbitrary number of arguments to our logger to print in the same way that we do to our print function. So for this, we're going to have to create a formatted string, which is not a big deal. Like so, and then the same with our draw, because we're going to have this dt as well. And our dt, we're going to set the precision to be no more or exactly 4 decimal places. And there we go. Now we're going to save that. And then when we run this time, see, before we just had draw, exit, and just this information. But when we run it now, assuming that there's no errors, of course there are going, missed out on little closing dash there. Now when we run, now we can see we've got our init, our size, our draw, which is looking a bit nicer now. And this is important because we can see if there's, if there's some sort of problem, if there's a huge gap here, if it's stuttering, seeing the DT can be very helpful for diagnosing any sort of big problems. and then we've got our exit at the end. But we've got all this extra information now. We've got the timestamp, we've got the log level, we've got the file that it was actually logged from, and we've got our actual message. And so this is really good. Like there's lots of information which we can, it tells us a lot about what's happening. Now, one cool feature is if I just bring up our utils here, if I want to not log all of the info, if I want to only log errors and nothing else, now when I run this again, it's not logging out any of that stuff. So we didn't have to go through and comment out every single one of it or anything like that. The great thing about using loggers in this way is that we can toggle on and off the information that we want to see with a very simple, just changing the level in one place. I'm going to leave the info on because we're going to be using that throughout the whole process. But there's lots of other things loggers can do, but this is one thing that, one of the reasons why I should be using them. Anyway, there we go. Now we can get on to the next part, and I'll see you there. Okay, now we want to load up some audio. So we want to be able to load audio files so that we can read the samples, read the audio data bit by bit by bit, and we want to have some playback as well. So we want to be able to hear the file, we want to be able to play it, and we also want to be able to extract the data bit by bit by bit, like live. Like we want to be able to grab that data because the next step after this is we're going to plot that data. That's why we created a window, so we can actually visually display everything. So we're going to create a source object or a class. So tree, so we can see it, we've got utils and window in our app so far, and we're going to create a new file called source. And we're going to build out a class that's going to handle everything for us. So code along, copy along. We're going to need to import, we're going to need to install some software as well, but we'll get to that. Subclass, our source. So we're going to have two different ways of taking input. We're going to take a file that's going to be one way, so we'll subclass our source, and there's going to be another way as well. We're going to take input from our microphone as well. Now we're going to implement our file first, and then we'll get to our microphone a little bit later. We're going to take in a file, and then we're going to take the data that we get from the file, and we're going to display it. We're going to output the audio wave in our window, and then once we can see it and it all looks good, and we can watch the audio wave while hearing our playback, then we're going to come and implement our microphone after that. So we'll get to that. Cool. Now we want to instantiate our file object that we just created in our main. When we call this particular file, our source file, so we do that with an if name is equal to main, then we want to play some audio. So we'll grab a file name. We need to grab a file first. So file name, that's the first thing. So the way I'm going to do that is I found something hosted by the University of Illinois, Chicago, I believe. And this is just a collection of sample files. I'm going to grab this one here called the Gettysburg. It's the Gettysburg Address for all of my American friends. We can listen to it
Years
now.
ago, our fathers brought forth on this continent a new nation, conceived in liberty and dedicated to the proposition that all.
So that's it. It's a WAV file. I believe it is a public, public use, all that kind of stuff. If I'm wrong, oops, I'm really sorry. But I'm just going to save that. And that's just going to save to my downloads. And once we have it, I'm going to come out here and we're going to create a new folder. And that folder is going to be called audio. So we're going to say make dir audio in tree. And so I've got a new empty audio folder here, and I'm going to copy that Gettysburg WAV into our audio. There we go. We've got it. We've got it here. We can use it, and you don't have to use the Gettysburg.wav. You can use anything you want. I'm going to put the link to that particular file in the description, and shout out to the University of Illinois. Now we've got that. Now we can load that up. So we're going to state the path, and the path is from here, from our root. So you can see, because we run our files from this root folder, we're not going to say just load Gettysburg. We need to, from here, specifically go audio/Gettysburg. Gettysburg.wav. Gettysburg.wav. Yeah, sweet. Now we create our source from our file, and we give it the file name, and that should do it. It will actually fail, which we'll see why. First, we've got to go to our make file, and we need to create a new. We just need to copy this target, and we need to change it from window to source. Save that, and then when we go make source, that's right, we need to install some software first. So we need to activate our virtual environment first. Source venv bin activate. We need to install PyAudio and librosa. And on Linux, you may or may not need to install the Pulse Audio package from apt. On Mac, you just go brew install Pulse Audio, no spaces. I'll show you. We'll make sure that we have it on Linux in a moment when this finishes. There's a lot of packages. Okay. And then sudo apt install Pulse Audio for a Linux machine. And I already had it. I already knew I already had it, but you will need that as well. And then if you are on Mac OS X, you're just going to go brew install Pulse Audio instead. Okay. Now let's try again. Make source. Okay, so that just worked, but the problem is it was running in a different thread, and our main thread is not waiting for, it's not waiting for the audio. So we need to keep it alive for that to happen. And all these printouts, these are printed to standard error. They're kind of annoying. I think we'll just keep them there for now. We can hide them, but it's kind of annoying. But I might do that later if it bugs me enough. So what we need to do is to keep this open and alive, we're going to use the time.sleep for 10 seconds. Well, yeah, 5 seconds. And what's going to happen is it's going to play for 5 seconds, and then the program is going to terminate, and it's going to in turn terminate the thread as well. So I'll save that and run source.
87 years ago, our fathers brought forth on this continent a new nation.
There we go. So it's working. We're able to load audio successfully, and it's okay that we can only use it in this weird way alone, because what we're going to do is we're going to use it in the context of Qt from our window, and our window will be the main thread that stays open, and then playing the audio on a different thread will be totally fine. It won't affect us negatively or anything like that. So yeah, the next thing we're going to do is we're going to create our app. We're going to subclass our window, and we're going to load up our audio, our file source here, and then we're going to start displaying an audio wave on the screen. So we're going to get to something visual and something awesome next. Now we want to make our main program. So we look at our structure again. We're going to make a main.py file inside of our app folder. So we're going to go nvim app main.py. And this is where we're going to do our work. So we're going to import our window. We're going to implement our interface methods. Actually, we won't implement our exit just yet, and we'll show something. We'll show why. And we want to run that using if name is equal to main. Should be as simple as that. Now when we run this, our window should work, and interestingly, we're not going to get any of our print, well, not that interesting, we should understand how this works, but we won't get any of our normal printouts except the exit function, because we overrode those 3 functions from our window. From our window. So this, and this, they're not going to be called anymore. Only the exit is going to be called. So we're going to go, we need to open our make file and create a new target. And then make, and it's the top one, so we don't have to add any arguments. And that's it. And then when we close it, we'll get the exit logout, but nothing else. Like so. Sweet. So now we're going to open back up our main file, and we're going to add our source. So our source is going to play as soon as we open the window. So I'm going to put that inside of our init. It's going to be file, and then our file name. We're going to swap this out for our microphone soon. We're just going to use the file while we're developing our the audio wave. But so we'll go audio. I think that's how it was spelled. And that's it. That should work just like that. So we're going to import it from source. Import our file. Let's try it.
87 years ago, our fathers brought forth on this continent a new nation, conceived in liberty and dedicated to the
Yep. She works. Sweet. Okay. Now we want to we want to be able to grab some data from our source continuously. So when we're drawing, when we are in our draw call, we want to grab a window, a small buffer of the sample data that comes from the audio data. So we want to go window equals get, and we want to grab a small window every single frame. Now I whipped something up that can help us sort of visualize what exactly this looks like. So if you imagine that between this tick here and this tick here, that this is 1 second. Let's just imagine that for a second. This is 1 second worth. Now this window, it has a certain window size. Doesn't really matter what that is for now. We want to grab on the first frame, we want to grab this window, and then the second frame, we want to shift over and grab the next one, and then shift over, and then shift and shift and shift. And what we can see here is that for every 6 frames, 1, 2, 3, 4, 5, 6, we want to shift exactly 1/6 of the distance. And this is called the hop. How far are we going to hop from here to here? It's called the hop size. And this is a concept that is important when it comes to our spectrogram, and we're introducing it here, but it'll become much more familiar later on. And so I made another one here with, you can see 3 frames per second. We've got the first window that needs to shift over a third, and then another third, and then another third again, and it will end up aligning with the start of this new second here after 1, 2, 3 frames per second. And so each frame, we're grabbing a chunk, a window of data. So I just thought it would be good to visualize this. And so this window, it should be, we'll print it out. It's going to be either a list, it's either going to be a NumPy array, or none. So we're going to go window.shape if, okay, so if the window is good, if it's not none, then we're going to call this property, and it's going to tell us essentially the size of our list. If not, we're just going to say none. Okay. Now, I don't think we've implemented our get yet, but we'll do that right now. We're going to need that window size and our hop size. We'll just give it a value of 450 for the time being. We're going to calculate it exactly, but we'll get to that in a minute. Cool. Now, hopefully there weren't any errors. Yep, there's an error right here. It should be if. Okay, and then now when we call this draw function every single frame, we should see, we should be fetching a window or none. So we'll see what that looks like now.
77 years ago, our fathers brought...
Okay, so what we can see is it starts off having a frame every single time, a window, but then it very quickly runs out. Like it very quickly reaches a point where it doesn't have any data available for that particular frame, and it starts happening very, very frequently. That's what these nuns represent. So if we go over here, what's happening is this hop size is jumping across too fast. Now, the actual hop size that we want, see we picked 450, just, pay attention, follow along, this is the important part. We initially picked a hop size of 450, but that hop size is too big for us. We can calculate what it should be exactly. Actually, we'll make our wave first, and then that should illustrate the point a little bit better if we can actually see it. We'll also add we want to calculate the number of buffers or windows that we have available as well. That will be really helpful. Let's do that. Okay, so we'll run the program again, but we will also grab how many buffers we have available. That might illustrate the point a little bit better. Okay, run again.
7 years ago.
Okay. So we started off here with, double digits number of buffers left, and then it's getting lower and lower and lower and lower and lower. And then when we have none, see, we have no buffers available. So again, our hop size is too large. And again, what we'll do now is we will show visually what that looks like. And then after that, we'll calculate our hop size exactly and we'll adjust it. And then this is an important point. So now we're going to actually get to putting something on the screen. Really fun part. So I'll just close down these for now. And we're going to make a new file and we're going to call it wave. We're going to put it in our app folder. And there's a lot to go in here. We're going to do some OpenGL programming right here. Okay. And we're going to have to import some, we're going to have to install some packages as well. So we're going to have to do some OpenGL shaders here. We're going to define them as text, and we're going to pass them to the ModernGL framework. It's going to make it really easy for us. Window size is going to be 1024. We only want to grab, say, the first 100 elements. And this is just an aesthetic choice. This is not super important. And you'll see why in a minute. And I'll just smash out the whole thing and explain it at the end. Okay, that was a lot. So to actually use it, we're going to go to our main file. We're going to need to import it. And create our wave. We have our context from our window, which I'll just quickly show again. In our initialized GL, we had self.context right here. We create this context. So when we call init, we have it available. And our wave, we needed the X, so its position on the screen basically. X, Y, it's going to be in the top. This is from the top left corner. The width is going to be the width of the screen, which we set to 1280. We're going to take all these values, all these hard-coded numbers out in a second, and we're going to put them in some sort of config file, and then we'll give it a height of 200. And then in our size, we want the wave to update its own size. We'll just feed that. And then we'll come down here. So we want to go wave, we want to add that window or null. We need to tell the wave to update. And we separated these because we might be calling wave.add multiple times per frame in the future. So we want to update that. And then we want to go self.wave.draw. And that should be everything we need to see something on the screen, hopefully. And we'll come back, we'll look at it, and then we'll come back and we'll explain everything once we get rid of all the errors. One more thing first, we need to install an additional package. So luckily we've got our env activated here. If not, just go source venv bin activate, and then we want to go pip install ModernGL. Oh, we already had ModernGL. Oh, never mind. Oh, sorry, we need peer. Pip install peer. Sweet. And then moment of truth. Yep, spelling error. I think I was supposed to capitalize something. I think it should be here. Yep. Capital V. Try again. Yep, forgot a bracket, curly bracket. Yeah, there was no way I was going to get through that without making a few mistakes. So what's next? Token GL position, okay. Yeah, no semicolon. P is not defined. Yep, that'll be down here in our size. We need a capital P. The wrong shape. Yep. So this should have been a -2. And the reason why we're doing this is because we have a big buffer of samples and we want to shift them over 2 at a time on every time we call add, and then make room for 2 more, which one upper and one lower, and it'll make sense to us once we can see it. Save, okay, yeah. Hopefully that's the last one. Instead of save, it should be a wave.
87 years ago, our fathers brought forth on this continent a new nation, conceived in liberty and dedicated to the proposition that all men are created.
Okay, so I believe it's working. It's just that our background shouldn't be as green. We need to change that. So we'll come here and we'll change this to, we'll just set it to black, so we can really see what's going on.
87 years ago, our fathers brought forth on this continent a new nation,
So we have
conceived in liberty and dedicated to the proposition that all men are created equal. Now we are engaged in a great civil war.
So why is it doing that? Let's figure that out. Won't need our window anymore. So why is that happening? That's why. This should be a multiply. Sample multiplied by half the height. Let's try one more time.
87 years ago,
There we go.
our fathers brought forth on this continent a new nation, conceived in liberty, and dedicated to the proposition that all men are created equal.
Now we
Now we
have
are
an
engaged in
audio
a great
wave
civil war,
traveling across
testing
the
whether
screen,
that nation
and it
or any
looks
nation so
awesome.
conceived and so dedicated can long endure.
And you can see here it has completed, but it still keeps moving across the screen. Now, the thing that I wanted to demonstrate before is that we have a few gaps. Actually, you know what? I'm going to change this, and instead of having a height of 200, I'm going to give it a height of I'm going to give it the full height, 720. This should look really cool. It'll be the full size.
7 years ago,
so
our fathers brought forth on this continent
wave
a new nation, conceived in liberty and dedicated to the proposition that all men are created equal. Now we are engaged.
Okay, so something I want to demonstrate when it goes across, I'm going to go back to our source and our hop size. I'm going to increase our hop size again. I'm going to increase it to 700. And now I want you to see what happens when I do that. The wave itself is going to have way more of these gaps, and these gaps will be represented by lines that I'm missing.
7 years ago, our fathers brought forth on this continent a new nation, conceived in liberty and dedicated to the proposition that all men are created equal.
And I'll do it again, and I'll make it 5,000 so that now it'll really, you only have one line per every.
7 years ago, our fathers brought forth on this continent a new nation, conceived in liberty and dedicated to the proposition that all men are created equal.
So the reason why
now we are engaged in
is I want to demonstrate that our hop size is directly related. Like the hop size, we need our hop size to be a specific number so that we don't run out. Here, we don't have any of these nuns. We don't want these, right? So we're getting heaps now. It's because our hop size is way too big and there's not enough data ready for us. And I'm demonstrating this with the green audio wave, but it will be way more important when we get to the spectrogram next. So this is why I'm just trying to make this point of like why picking our hop size is so important for the display purposes. And the hop size that we use here, it will be the same hop size that we use in our spectrogram, which is an important concept as well. And so I'm just trying to really get you very familiar with the hop size straight away. So the actual hop size that we want to use, so we calculated here before, it's hop size equals the total number of samples, which is 22,050, divided by the frames per second, which is 60. So we're going to just open up a Python thingamajiggy here, and we're going to say 2250 divided by 60. And that is the perfect hop size for us to use. Now we're gonna round up. We're gonna use, say, we use 370 just to be safe, because there will be a little bit of a delay, a little bit of a buffer. So we'll go 370. That means we should get almost no nuns. So these nuns here should be almost 0. So we'll try again.
7 years ago, our fathers brought forth on this continent a new nation, conceived in liberty and dedicated to the proposition that all men are created equal.
Or practically no gaps.
Now we are engaged in a great.
We'll hold here, and we can see we're getting zero nuns, right? So this is why we wanted to do this, and the number of buffers, or the number of windows that we have available at any one time, stays roughly at around 10. It does seem to be shrinking slowly. So if we start up here, we can see it's double digits. There's a lot more of them. And as we come down and down and down and down and down, it starts to reduce really, really, really slowly. That's because we round it up. So I'll do it again, and it will eventually get
7 years ago,
so see,
our fathers brought forth on this continent a new nation, conceived in liberty and dedicated to the proposition that all men are created equal. Now we are engaged in a great civil war, testing whether that nation or any nation so conceived and so dedicated can long endure.
Okay, yeah, we ran out of data there. So yeah, so that's because it reached the end of the thing. So that doesn't count. But this hop size is almost perfect and practically perfect for our purposes. And what we actually do as well is in our, actually, yeah, we'll just keep it like that for now. Close this down and go again so we can see our beautiful
7 years ago,
wave.
our fathers brought forth on this continent
And
a
that's
new
it.
nation,
That's our
conceived
wave
in liberty and dedicated to the proposition that all men are
now,
created equal. Now we are engaged in a great civil war, testing whether that nation or any nation so conceived and so dedicated can long endure.
And then we can get started on our spectrogram, which is, the real fun part. Actually, no. We don't want to do that yet. We want to add our microphone. That's what I was supposed to do. Yeah, so we'll get to our microphone now. Okay, we want to get our audio from our microphone instead of a file now. So we'll open up our source. And we already have most of it. So we've got our file, we just need to fill out our microphone. And it's pretty simple. It's going to look almost the same as our file. It has an init and it has a callback. It's just that it's not going to load all of the data up front like it does with the file. It's going to fetch it continuously. Okay. That should be it. So now we want to use it. So we'll open up our main file and we'll import our microphone, and we'll come down to our source and we will comment out this file source, and we'll just swap that to microphone. And that should be all that we need to do. And now when I run the program, what should happen is it should pick up my default microphone, which should be the one that I'm speaking into now, and you should see the audio wave of my actual voice. So let's see if that works. And it looks like it is. That definitely corresponds exactly to, this beautiful voice. So yeah, so now we're getting input from our microphone. We have the ability to get it from our microphone, and we also have the ability to get it from a file. Now for the remainder of this, we'll probably be using, for the remainder of this, we'll probably just be using the microphone. We probably won't be using the file anymore. And the microphone is like a lot cooler anyway, in my humble opinion. So next we need to get to our spectrogram. But before we do that, we're going to separate out some values, our constants. We saw we used our buffer size and our hop length and the window size and all that sort of stuff. We're gonna take out all of those hard-coded values and we're gonna put them into their own config file. So we'll do that. So you can see we've got our project structure here. We're going to make a new file. We can do it inside Vim. So we need to go tab edit and we can go, we want it to be app config.py. I'll save that and I will treat. So it's inside of our app folder, just in case anyone's not using Vim. So we're going to need to collect those values. So we've got 4 of them here. We'll just cut all of those out and stick them in here. We also need to go to our window and we're going to make a window width and a window height. And I'll just like to make them a little bit more readable. And then we need to go and replace them. So when you go up here, we're going to import our config. Replace these two. We just go config.window width. Now config.window height. And I think that's the only place that we use it. Yep. So our window is done. And in our source, we need to do the same thing, import our config. And just go through each one. Wait. And so our source is done. And in our main file, I remember we used it right here as well. Config.window width. And this is just in case we want to change our window size or anything later, we can do it from one single location. Big. And I think there was one more in our wave. Oh no, we don't need to put it in here because it's past here, our width height. We don't actually need to grab here. So get rid of that. Sorry about that. And close down all of these. And then when we run it again, should work perfectly well. And it does. All right, now we've cleaned that up a bit. Now we need to get to something really important, and that is our spectrogram. Now, I'm not just going to jump straight into, I'm not going to make the spectrogram straight away. First thing I'm going to do is I'm going to open up a Jupyter notebook and I'm going to explain, I'm going to use the librosa library to create a spectrogram, and then I'm going to, basically we're going to recreate that spectrogram in a way that's going to allow us to create one that's continuous that scrolls across the screen. And I feel like it's important to explain how it works, where we got it from, why we're trying to do what we're trying to do. And then once we do that, then we'll come back and we'll implement it. You don't need to code along for the notebook, but I felt like I needed to explain this particular part. So we'll get to that next. Okay, no need to follow along with this part. I'm going to create a Jupyter notebook and I'm just going to visually display and explain a few things. Okay, so first I need to install Jupyter. And then run my Jupyter notebook. I'm not sure if you've ever seen one of these before, but it's really simple. And it'll open up a browser and it will give you something like this. And I'm going to create a new notebook in the root of my project. And you'll be able to go and look at this notebook in the repo that I create at the end. So we've loaded up our Gettysburg file, and we've just got 10 seconds at this sample rate. So we've got this number times 10 individual samples. And we're going to plot our audio wave first. Might have an error, I might have to roll back my version of matplotlib. I had some problems with it before. Yeah, okay. So what I'm gonna have to do is I'm gonna have to, this is not important. This is just, okay. Fix that. I had a, and the version of matplotlib that I had, I just had to roll it back by one. There was some issue with it. Anyway, now we can see our audio wave. And so this is what the data actually looks like. It's the first 10 seconds, as you can see down here. Okay, so this is our audio wave. We want to turn this into an audio spectrogram. Now, librosa provides us a really easy way of doing that. There we go. So this is an audio spectrogram. So what we can see here is, so this is our wave, and you can kind of see how this loosely corresponds. So you've got a big, like lots of activity down here, and then a big streak, lots of activity down here, sort of some big streaks, and they sort of roughly correspond to big streaks here. Now, what this image represents is, it's a three-dimensional plot. We're going to change the color of it because it's not very easy to see. And this is my favorite color scheme, and it's the one we're going to use later. So this is a three-dimensional plot. Basically, we have the time axis along the bottom. We have the frequency axis along the top, and where we have this X and Y meeting, the intensity of the pixel represents the frequencies present at that time point. So, as we go up at this time point, exactly 1.5 seconds, the intensity of the pixel at each frequency height represents the presence of those frequencies at that time point. And so the actual color, this represents decibels. And so you got, down here, negative 50 decibels, that's really quiet. And then 20 decibels, that's, that's moderately loud. Like you can hear that. And so this is something that's generated for us by librosa, and it's great. But the problem is we want to make a live spectrogram. We want this to scroll past continuously. We don't want to load in a file and load it all up at once. That's not what we want. We need to figure out a way to take this, what this does, or this exact functionality, and we need to replicate it so that we can compute a single strip at a time. And then the next time point, we'll compute another strip. And the next point, another strip. And so we can have it scrolling along the screen at a frame rate that we specifically want and we can choose. And we just want to be able to feed a small window. Remember, we've got our windows. We want to feed one of these windows and then have it compute a slice of our spectrogram. So that's why I showed this before, because we're going to be using these overlapping windows, and you don't want to, we definitely want some overlap. This is just the part of the way that this is calculated. And librosa is doing a lot of this stuff internally as well. That's why I sort of introduced that sort of, scroll, like sliding window concept. So what I'm going to do is I'm going to type out everything we need to replicate this exact functionality, but in a way that's going to allow us to do it slice by slice by slice. We're going to create a few functions in here, and we're going to reproduce exactly this in our different method. We're going to create an image that produces exactly this spectrogram. So we're going to create that image, and then the functions that we create to do that, we're going to copy paste them into our project. And so we're going to have everything we need from there. But I just thought it would be important to show what we're doing, how we got to this. So if you want to go and look up librosa, this short-term Fourier transform, what does that do? How does that work? You know, you can, I thought it was important to show you where this came from. You know, I didn't just pull it out of me. Okay, one of the first things we need is something called a Hahn window. And NumPy creates one for us. Oh, sorry, not a Hahn, a Hanning window. I just call it Hahn just for short. And what does this look like, you ask? It's this particular shape. And you can look this up further. You just go to Wikipedia, Hahn function. So it's this function that is used to essentially, I'll show you in a second. But if you want to look up this a little bit more, you can come there. Now, what we want to do is we want to I'll grab a section, I'll grab a window of our data. So that's the first thing I'll do. So I'll grab, say, the 20th window. So the way that we do that is grab that slice. So from the from our window size multiplied by 20 to window size multiplied by 21. So we're going to grab essentially the 20th window size. I'm sure you can see how that gives us what we want. I'm going to plot that. So this is just a small section of our audio wave, one window's worth. And you can see, the sort of repetitive, pattern. This is only about 1/20th, roughly, about 1/20th of a second, because it's 1024 samples long, and we have a sample rate of 22,050 samples per second. So this is about 1/20th of a second, roughly speaking. Now, what we want to do with our window is we want to turn this signal into a sort of wavelet. We want to multiply these two, and I'll change this. Give me 1 second. Change that color there. So we want to multiply these two lists that are the same length, 1024. We want to multiply this one by this one, and I'll show you what that result gives us. So we want to taper our signal. So we want, basically at the edges, we want to lessen this, the edges, and we want our signal to be concentrated in the middle. And this is necessary because of the way that the discrete Fourier transform, or the fast Fourier transform works. The fast Fourier transform will give us, actually, let's have a look. So sure we can find an image that shows us. Found a good one the other day. Okay, here's a good one. So what we have here is our signal image. What we have along here is our signal. Now what we want, so this is the sort of the time domain. You can think of it as that. So as it goes tick, 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 it's moving along in time. Now, but what we want, we have our signal in this form. We want our signal in this form, which is the signal, the frequency domain, sorry. We want to know, see, we've got a signal here, so it's a spike, and then another signal here, it's a little bit not as strong, so it's a little bit less, a little bit less, a little bit less. So the Fourier transform allows us, actually this is a much better one. The Fourier transform allows us to go from the time domain into the frequency domain. It also allows us to go in the reverse direction, potentially as well. So it allows us to do lots of fancy things with signal processing. But what we are interested in is going from the time domain to the frequency domain. So we want to take our small section of a signal and we want to figure out all the frequencies in that tiny little signal. Now, we can't just give our entire file and figure out what frequencies are in it, because we won't be able to tell at time t what frequencies, time t plus 1 what frequencies. It's just going to be one jumbled mess. So that's why we need a tapered section, a tapered window, and then we feed just that tiny little window and figure out what frequencies are just in that little slice. That's why we're sort of going through this annoying process. And I hope that I am explaining it, somewhat. You're not going to be an expert in this. I'm certainly not an expert. But you should have enough to understand at least roughly what's going on. So I'm going to plot our tapered signal, and I'm going to plot our Hahn window on top. So we'll see what that gives us. And let me just fix that. Okay, so see, this was our signal, right? Where the edges, it's really pumping. But what we've done is we've created a sort of wavelet. We have tapered off the edges so that the frequencies are really pumping. We care about the frequencies more so in the center than on the edges. We want to sort of quieten those down so that we can just see what's going on in this little packet. So that's why we do that. And that's like just the setup. That's what this little Hahn window does. We'll see sort of how that fits together. So sometimes our window might not be the full 1024 or the window size length. In that case, we're going to pad the rest of it with zeros so that we're always going to have a window that is of the right size, but we'll be able to pass it a size that is less than that. And then if it's the full length, then we can just continue on. We just need to taper our window and then perform the fast Fourier transform on that, which is going to pluck out our frequencies from our short little wavelet. And NumPy contains all these functions for us. We don't have to write them ourselves, and we probably shouldn't, even if we wanted to. We can, if you guys would like to see that. I reckon that would make a really fun video. But NumPy and other packages, they have like really, really fast, really, really efficient implementations of this. So, there's no need for us to write it ourselves unless we're doing it for like educational, fun purposes, which does sound like fun. So we're going to be able to clip or specify the minimum and the maximum decibels for our signal, because see the sort of range of colors or the range of decibels, we might want to clip. We might want to just throw away anything that's too loud, and anything that's like below a certain level, we might just want to throw that away so that we can have a consistent sort of tone for our spectrogram. So that's why I've included these. And that one was -50. I think max dB was 30. So we just set those as default. So our slice, we need to get the absolute value, the magnitude, and then, or the amplitude, and then we can convert that to decibels with libRosa does that for us. Remember this slice, this is going to be, it's going to get this for us. So we're going to grab a slice and we're going to feed it straight to our color. And we want to scale the full range. So the minimum to the maximum, we want that between 0 and 1. So we shift whatever the min is, could be positive, could be negative. We shift that to the 0, and then we divide by whatever the total range is. So the maximum minus the min, and that'll give us a range between 0 and 1. And it's going to be important for the next step so that we can pass it to our color map. That we brought in before. It requires, it's going to need something between 0 and 1. And once we get that, we're going to convert it to RGB pixels. And it's really easy to do. We'll multiply it by 255 so that we have, 8-bit, pixel values. And this should give us an RGBA image, but we only want the RGB. So we're just going to slice that. We'll return our slice. Now we are going to take this, our XDB, whatever that is, we're going to make an empty two-dimensional array of exactly the same or roughly the same size, but with a pixel channel. So we're going to loop over all of our slice. We're going to loop over our entire width of our image. So we're going to go all like this entire way, like this entire direction. So we loop over the width, and we're going to compute our slices. And we update that slice. And should be it. And then we check out the shape of our Y, which is our image, and we can display our image. We're just going to need to use the package pillow, which we should already have installed. And then we can just go image.fromArray, which is what our Y is. And there we go. Now it's upside down. So it's this. What we'll do is we'll grab this and we'll display it. Now I'll change this size. We'll display it right underneath. Change this, make this a bit bigger. So there we go. Looks very, very similar. What we'll do, we'll reverse this. That should do it. There we go. Okay. So now, if you look really closely at these two, they are practically identical. Like, they are absolutely bang on. Like, they're almost exactly the same. And I mean, I seriously doubt you'll be able to see any like visual differences between them. And so the whole point, so this is the one that was generated by LibRosa, and this is ours. This is our image. Now the beauty of this is we can compute it slice by slice using these functions. So that is the whole point of like why we've done this. And this is how we got there, right? This is all the different steps, what's involved, all that kind of stuff. Now we've got what we need. So we can take these functions, these two, slice, or we can combine them into one function, that's fine. I don't really see, there's not really any need to separate them. When I came up with it initially, I tried out lots of things, that's how I ended up with, but we could combine them. Yeah, 100%, that would be cool. And we're going to take these and we're going to stick them in our new spectrogram file, just like we created for the wave. We're going to create one for a spectrogram, and we're going to include these functions, and they're going to generate everything for us. So when we add a window, it's going to compute everything for us, and then it'll be really, really sweet. So again, you didn't have to code along with this. I just felt like it was important to show where I got this from, how I came up with it, all this kind of stuff, and some background on what's going on under the hood in case you are interested. So now we're going to get back to coding, and we're going to get back to our spectrogram, and we're just going to smash out the rest of it. It's going to be super fun. Let's go. Okay, and we'll move this out of the way, and we'll close down our Jupyter Notebook. Now we will run our app again, just so we can remember where we're up to. Looks pretty good. Sweet. So now we're going to make our spectrogram. So we'll look at our project structure. We're going to make a new file, app/spec.py. We had inside of our wave, we had this orthographic function. We're going to stick that. We're going to stick that in our utils file. So we'll stick that down here. Grab our two functions. I don't like using spaces, I use tabs. It's just my style. Now the height, we come back here. Where is it? Okay. So, yeah, here we go. So our y, our image height, or the height of our XDB, is exactly 513. And the reason for that is the fast Fourier transform has a window size of 1024, and it effectively halves that. It throws away roughly half the data. And we're left with a height that is exactly half, which is 512 plus 1. So this is where we get this 513 from. So we need our texture to be also have a height of 113, and then the width is going to be just the width of the window, which we're going to give it, which is going to be self.width, and then the number of channels. So that's where we get that number from. We're shifting our frame over to the left in exactly the same way that we did with our audio wave. Okay, so now we want to import that into our main class. Hopefully we didn't make any mistakes, but almost certainly did. I can see one mistake already. Got to be big. And another one here, config. Because we copied that over. And quick check. Looks pretty good. So we'll save that and we'll open up our main. Not that. Our main. And we'll have to import it right here. Import our spec, and then we'll load it up in exactly the same way as we did our wave. And yeah, we're going to drop this size of this one down back to 200. And the y, we're just going to give it the self.wave.height. So that way it's going to start at the bottom of the wave always, no matter what size it is. And this we're going to give a size of, or a height of 460. And a size, we need to add that here as well. And add it to our spec. We're going to update our spec. And then we need to draw our spec as well. And that should do it. Give it a go. Save and run. Yep. Okay, there's, yep, little error there on 109 in spec. So go back to spec and then just jump straight to 109 right there. Get rid of that W. It might be the only error. Wow. No, of course not. Slice 102. Oh, yeah. Okay, so if it's not none, they're going to create a slice. If it is none, then we're going to say slice is equal to self.slice, just for now. Hey, okay. So another error here on 104. I'm not broadcasting a shape correctly. That's because silly. There was always going to be a million errors. Okay. Wow. Okay. That is not working the way that it should be working. Okay, why is that? It's moving way too fast, for one, and it's weirdly broken. All right, it's gonna have to take me, it's gonna have to give me a second to figure out what's going on here. Again. Okay. What could be causing that? It doesn't make any sense. Ah, that's why. I've mixed up these two. So the width is supposed to be the width. So it's width and height, not height or width. Okay. Okay, should work now. There we go. Okay, so as I'm speaking, you can see that the wave and the spikes in the audio here and the spectrogram highlight at exactly the same time. Well, roughly speaking, like you can definitely see there's a correlation between these two things. You know what I mean? It's not an accident. They definitely are, working together. And that's what we wanted. Now, the only bad thing about this is that the microphone that I'm using is, it seems to have a lot of background noise, a lot of like feedback or something like that. That's why it's lit up like a Christmas tree. But apart from that, it's looking pretty fantastic. We can definitely see as we're speaking, or as I'm speaking, that we're getting the spectrogram, like we're getting the spectrographic representation of the audio as well as the audio wave, and it looks absolutely amazing. So that's the bulk of what we needed to do. Now the rest what we need to do, we need to add time and frequency axis. So we need time axis along the bottom and then a frequency axis along the Y. But that's pretty much the bulk of what we needed to do. So, you know, we're in the home stretch now. We will get back to that. And I'll see you in the next one. Okay, home stretch. So first thing, so we noticed earlier that our spectrogram is lit up like a Christmas tree. It is way, way too bright for my liking. So how we're going to deal with that is something we already implemented. So we'll go to our app/spec and see these min-dB, max-dB. That range that we basically we want to clip out, which we do here. We clip out anything that is less than or greater than that range. So let's try a range that starts from -40 decibels instead. And let's see if that is less bright or less overwhelming. Okay. It's definitely better, as we can see. So the background, it only has a little bit of, you know, a little bit of noise here in this background. And so different microphones and different volumes and different, you know, amounts of feedback and all this sort of stuff, songs that have, you know, the volume slightly more or slightly less, they probably will saturate in different ways. And so this is why I provided the ability to set this range or clip out this range. And it, you know, as you can already see, we've definitely got a much clearer signal here. I'm going to adjust it a little bit more, and I think that'll make it perfect. So I'm going to go back here, and I'm going to go -30 decibels to +30 decibels. I think that'll do it for my setup anyway. And look at that. So the background noise is almost nothing, and the only you know, pixels with any intensity, this is a much clearer representation of my voice as we're listening to it right now. So I actually like this. I mean, this is pretty dope. I like this. I don't see myself changing it from here. I really like this. This looks like an extraordinarily clear signal. So yeah, we cleared that up, and it looks beautiful. And you can see as well, if I try and, I'm going to try and sing, which I shouldn't. I'll try and hit like a note, like a he. Oh my god, that was so bad. But you can see that sort of, see these like almost like in harmony, these like different frequencies that are like fixed distances apart. So you can see there's a few more there. I don't want to do it. I'm way too embarrassed to try and sing again. But you know, you can see some really interesting patterns in this spectrogram. So yeah, we're gonna continue. And yeah, not much to go now. We're just gonna add a few details, a few things. We're gonna speed this up. That's one thing we're gonna do. We're also gonna add the time axis and the frequency axis. So let's keep going. One thing I want to do is see this. We're printing out. I don't want to print. I want to log. So get rid of that. I'm going to open up. I'm going to go to our app main. and I'm going to import our logger. And come down here, and I'm just going to swap this out. I'm going to go logger info. We're going to need a formatted string. There we go. Much better. It's pretty good. Yeah, and so if you like, there's lots of different sounds that have like definitely distinct, distinct patterns, which they're really cool. I've played around with this a lot. I've seen, I've tried to sing, I've tried to whistle, I've tried to, all sorts of stuff. Okay, so there's one other thing I think I forgot to do earlier. Remember when we go to our window and see we created this exit. So I want to implement this exit, and I want to clean up our source when we close. So I'm going to go here, I'm going to go exit, and I'm just going to go self.source.release. Save that, and we go back to we're going to go over to our source. Let's make sure we've implemented that release function, which we have not yet done. So in here, that should work. And I'm going to take these functions, these logs, and I'm going to stick them in here. And I'm going to do the same thing with our size. And the same thing with our init as well, just so that we don't lose those logs. Cool. Now when we go again, sweet. Now if I scroll up, you can see, our init, and then all this comes from our initializing our PyAudio, and then so now we've got some of that cleanup out of the way. We're going to get back to creating these panels. So we're going to create like an axis along the the bottom, and then one along the side. So first thing we're going to do, we're going to create a rect class. So a rect type of node that we're just going to render essentially a straight background of color that we choose. So we're going to go app rect.py to create that new file. And this one should be pretty easy. Okay, hopefully there's no errors there. Looks good, but it always does before tragedy strikes. Okay, so go to our main, open up our main file, and then we need to import that RS. So it's going to go from rect import rect. And so our panel color, we'll set it as that. So Let's see what that looks like. We need to come down here and go R1 dot size, set our width and height, and we need to draw that as well. And that should work, but errors abound. Yeah. Okay. I'm going to open up rect numped. It's not numped. Config width. Config has no attribute width. Sure about that? Config window width. Window width. There we go. Okay, so we've got this blue rectangle now, and that's going to be like a panel on our little interface here. So we're not setting the color yet, it's just the default color. So we'll actually pass the color now. Now we're confident that it's working well. Background color. Try it again. It's much nicer. Cool. Now we'll make the horizontal, the y-axis background. So copy this, make another one. Frequency axis background. Let's call this R2, and then the size, or the dimensions of that. So the X and the Y is going to start from the top left corner. The width, we're only going to give that a width of 80, and then the height is going to be the full height of the window. And then we're going to have to do this as well. R2, R2, yeah, that's it. Try again. There we go. So we've got our axis, our background along here, and our background along here. Awesome. Now it's starting to, look like an actual sort of, some sort of interface. Now, before I continue, it looks pretty good. Oh, see that? See that little whistle there? That was such a weird, I just love looking at this. Like, I could look at this all day. Anyway, so we're gonna, there's something I wanna, there's a massive improvement that I want to make to this app. See how every time we add a new object where, we're repeating ourselves, we're doing, wave.size, everything .size. We're doing .draw. This is a bit cumbersome, and we're going to be adding quite a few, we're going to be adding a few more items here. So I'm going to do this in a much better way. I'm going to create a list called nodes. It's just going to be an empty array. And then instead of, instead of repeating ourselves over and over, we're going to just add our objects, our nodes, to this array. And then we're going to draw everything in that. We're going to draw all of our nodes at once. So we just need to add them. So this one, we don't even actually need to hang on to this at all. We're just going to go self.nodes.append. Same thing here. Then what we can do here is we can get rid of all this. We can just go, and we can go node.size width height. Done. That's all we need to do for size. And this is going to grow to like 10, different items. And so we don't want to be repeating ourselves at all. And we're going to copy this, and we're going to stick that there. And we're going to be able to replace all these as well. So we go node.draw. Now we still need to update our wave and our spectrogram and update and all this kind of stuff. We still need to do that, but they're those two are specific to those two elements, and all the other elements like the text that we're going to add and the ticks for the, you know, the access, all of those, we don't want to be specifically singling them out. We just want them to be done automatically for us. Okay, now made those changes. Let's see if it still works. And it's still drawing exactly the same, but now it's, you know, it's a lot easier for us now. We just add it to our list of nodes and then we are done. Okay, so let's continue. So next we want to, let's clean up, you know, let's close down some of these. App window, we don't need that. Now I'm going to, let's have a look. Hello. Wow, it looks so cool. I never ever get tired of it. So awesome. All right, so now we're going to make some ticks along here. So tick, 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 some tick marks. And then we're going to add our text. So we want some dashes to indicate 1 second, 2 second, 3 second, 4 second, all that kind of stuff. So the way I solve this, let's look at our project structure. I created a new node called ticks, and it's a class that allows us to create both horizontal and vertical ticks of any size that we want. So I'm going to create a new file, ticks.py, and we're going to build that. Okay, now we've got that. Hopefully no errors, but there always are. We want to open up our main, not our makefile, our main, and we want to import that. Import our ticks, and then underneath our backgrounds, okay, let's give that a whirl. Yep, first error. Here it should be int, not init. If you caught that, you're a legend. Try again. There we go. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. So those ticks are they're exactly 1 second apart, because we're running at 60 frames per second and our gap is 60. So it basically means 60 pixels, and we're moving across at 1 pixel per second. So if there's a tick at every 60 pixels, that means there's a tick at every 1 second. So that's what that means. Now, if we change the speed, of this later, which we will, we're going to have to adjust our ticks as well. So keep that in mind, but we're going to give them a much better color. Nice. And we're also going to add intermediary ticks. So we're going to add ticks that are in between as well, just to make it look a little bit more aesthetically pleasing than that. So we're going to take our 1 second ticks and we're going to stick them underneath. So they're going to have to go first. Here we're going to go 1/10 of a second ticks. And it's going to be largely the same, except the height of it is going to be 15 instead. The color is going to be a little bit, just a tad darker. And the gap is going to be 6 instead of 60. And let's take a look at that. There we go. Now that looks really awesome. I really like this. Like, this looks great. So the next thing we want to do is we want to add some text. So we want to add, 1 second, like 1s, 2s, 3s, 1 second, intervals every second, text indicating the number of seconds at every time point. And this fits perfectly in here. You can see this fits snugly. This was, there's no accident. I picked all of these numbers so that it would fit, very, very nicely in here. But yeah, next thing we're going to do, we're going to add some text. Now, text in OpenGL is quite annoying. It's pretty involved to add some text, but I've wrapped up all of the functionality in a class, and just like any other class, like our rect, like our spec, anything like that, we're going to create some text, and we're going to need to import a new package, the free type package for Python. That's going to allow us to work with text really easily. And I'll show you. It's not really my, I'm not the first. Like, this method of using text is sort of a common way that I've seen in both Python and in C programming, adding text to OpenGL. But this is just my sort of flavor or variation of it. And you can, I'm sure you can take my class. You can do it. You can use it in the future. That's why I wanted to show this app and to add the text and to add all these extra little bits and pieces, so you can see how to program something like this. Like, how do you put it all together? How do you, it's no good just knowing one small section of it. You want to put the whole thing together. You want the complete package. So now we're going to add some text. So let's do it. Okay, so for that, we look at our structure and we want to create a new file again. And we're going to call it text. So we go nvm app text.py and follow along. Actually, before we do that, we've got our we want to install our pip install freetype -py. Sweet. And then we can continue. This is a link to a Stack Overflow question where I got a lot of this from. So I just thought it was good to reference that, and this will be in the repo for anyone who wants to check this out later. Okay, that was a lot. Wow. Let's look over it quickly, make sure we didn't make any obvious mistakes. Looks pretty good. Okay, we're going to save that and we're going to close that file. Now we look at our project structure. we need to make a new folder and call it fonts. We need to grab, we're going to open up a browser window and we're going to go to Google Fonts. And we're going to browse. Now the font I like to use, you can use any font you like, any font you want, but you might have noticed that I picked one called Rubik, right there. So I'm going to click on that. I'm just going to go download family. Cool. And static. The one that I actually want is just Rubik regular. Just going to extract that to my to my downloads folder. Cool. Close. And I'll move that away now. And then if I look at my downloads folder, there we go. I've got this Rubik-regular, and I want to move that into our new fonts folder, that we just created. So I'm going to move downloads Rubik- to fonts, and then we tree again, and there we have it. It's right where we want it. Easy peasy. Okay, now we'll come back to our main file, and we need to import our text class from text import text. And then I'm going to come down here underneath our ticks, and we're going to create our text. Now our text is a little bit different because we're not going to create a new node for every single character that we're going to write, that we want to display. We're going to do it in a different way. So we're going to create our text here, and we're just going to create that object we created is just going to be a text renderer. So that's all it's going to be. It's going to render our text, but it's not actually going to, as I said, we're not going to make one object for every character. That would be silly. So create our text, add it to our nodes, and then under here we're going to actually add our text to it. So we're going to add a bunch of different things, and it's going to loop through all of the text that we've added, and it's going to render them all in one go. Render 20 seconds from now. So the text we're going to add, it's going to be a formatted string, and it's going to be the I, the X, the Y is going to be 705 to line up with everything we want, and the alignment is going to be center. We're going to center align out these particular text, these particular characters. Not characters, it's because I was going to have characters. It's going to be the number and then a little s next to it, and that should do it. So we've added our text object, and then we are adding a bunch of text to it. And then our size and our draw, it should draw everything that we want, assuming we didn't make any mistakes. And we should never assume that because it will make us sad. Okay, so there's a problem with the shader that I just created. So the text shader. So there's definitely a problem in here somewhere. Give me a second. So one problem I've got here is this mask. I want to go .r. So this might not fix it entirely, but that's definitely one error that I forgot. Try again. Nope. So undefined variable image. Okay. Sample should be sampler 2D. So that's probably why it doesn't recognize that image. Yep, is instance. We spelt that, well, I spelt that wrong. Not going to blame you. Is instance. Try again. Height is bitmap, has no attribute. Height. We sure? Let's have a look at that. Ah, yeah, that's not height. It is rows. That's my mistake. Character slot object, no attribute context. Yeah, it's not self.context, it's just context because we're not hanging on to that context. And character slot and int. Okay. So I can't use this bit shift on character. Yeah. Okay. So that's on line 130. 130. Yeah, it's not character, it's character.add advance. Try again. There we go. Okay. So we've got our little, it's obviously a huge problem with it, but we're making progress. So the problem with this is that we need to give OpenGL a setting that's going to allow it to blend, because it's not dealing with semi-transparentness. It's not dealing with alpha channel very well at all. That's why all these texts look like little blocks. It's drawing the whole little texture. It's not actually drawing just the text part. But we'll fix that. That's only one, super easy to fix. We need to go to our window where we set up our OpenGL, and there's something we need to add in here. We didn't need it before, but we do now. So that is underneath our clear. It's going to be self.context.enable ModernGL.blend. And that should do it. We might need to add something else, but there we go. Alrighty. So we've got ticks. How good is that? And we've got our little text along there as well. Awesome, awesome, awesome. We're missing the 20th second. Oh. No, it's fine. We don't need that one. That's totally fine. So that's it. Like, we've added our little tick axis and it looks brilliant. It looks amazing. Now we have pretty much everything we need to go and add our frequency axis, and we'll do that now. So as I said, we already have pretty much everything we need. We can close down our window. We don't need our text anymore. We don't need our ticks anymore. Now, we've added our frequency background. Now we need to add our frequency ticks. Now, again, we've already created the object that we need to do that, our ticks object. We just need to create a somewhat elaborate tick object. So we'll do that just under here. New ticks. This will be our 2000 hertz ticks. So we'll have ticks at every 2000 hertz. We won't have too many of them. So we need to know how many pixels high is each frequency. Right, so up here we've got our spec, which is 460 high, which we've got. So it's 460 pixels high. Now our frequency range is exactly 11,046. Now that number comes from, I'll explain that in a moment, but we need to get our number of pixels per frequency. So to calculate that, we'll create a value called pixels per freak, and it will just be self.spec.height divided by 11,046. 11,046. So, and that's because this 11,046, let's run this. So our frequencies starts from 0 down here, and then it goes up all the way up to about here, the very, very top of this this texture, this frame, our spectrogram. It goes all the way up to 11,046. That's the full range that we have, and that number comes from where did we calculate that? It has to do with the frequency resolution, and there's an equation for it. It's not really important, but basically the equation is it's the sample rate divided by the window size times the number of spectral lines. And the number of spectral lines is that 513. And it's kind of an annoying, like it's not really necessary to understand. I don't even know why I tried to explain it. It's overloading too much about how the fast Fourier transform like does its thing like internally, which, you know, as I said, I'm not even an expert. I've learned enough to know how to build this sort of thing. But this number, if you want to look into this further, you will be able to figure out exactly where this number comes from. And if you guys want me to create a series on how to implement the fast Fourier transform from scratch, like that's the only thing, that's a series where we build the entire thing from scratch, something I've never done before, would love to figure it out. Let me know if you want to see that, and we can learn together. We can go through it together. But so we just need to, the important thing is this number represents our total frequency range, and we need to figure out how many pixels per frequency. And so we're going to add a new ticks object, self.context. The x is going to be 70, and we're going to need some more room here. This is going to be a bit messy, this one. Our y is going to be our spec y. Okay. So what we've done here is this y, we want the top of our ticks to start from, because we want ticks that go from the very bottom of our spectrogram all the way up to the 10,000 mark, right? So we need our spectrograms, this is the top, this is the top of our spectrogram. We need to shift it down by exactly this amount. You can see, and this is, 1046. If you take 1046 away from this, you get exactly 10,000. That represents the top 10,000 mark. And then the height of that is this number of frequency pixels for a range of 10,000. And then the gap is for a range of 2,000 of these frequency pixels, which basically means that we're going to have one tick every 2,000, every 2,000, let me start again. We're going to have one tick every gap of 2,000 frequencies. So we're going to have 0, 2,000, 4,000, 6,000, 8,000, 10,000. They're the only ticks we're going to have. Sorry for the, I'm not very good at explaining things. Anyway, that should work for us straight away. And yeah, so this is probably a lot more clearer, a lot clearer. So this is 0, this is 2,000, this is 4,000, 6,000, 8,000, and then 10,000. But the actual spectrogram comes up to about this height, roughly here, something like that. As you can probably kind of see. Actually, I'm going to put a line there so that it's a little bit clearer. I'm going to come up here, and I'm going to come to I'm just going to grab one of these. And I'm just going to stick it here. And I'm going to go, I'm going to call this the wave spec separation line. Okay, something like that. And then this is going to be, the height is going to be the self.wav.height. The width is going to be the full width. The height is just going to be a few pixels, something like that. And then the background. Okay. Let's try again. There we go. Okay, so now we've got a line here that separates the two. So we can see here we've got this is 8,000, 10,000, and then the total height. You can kind of imagine that this frequency at the very tippy top is 11,000 as a frequency of 11,046, and so that's that's why we've put ticks like this, because we want them at nice whole numbers. Well, 0, 2,000, 4,000, 6,000, 8,000, 10,000. Okay, now let's add the actual text for those. So we come back down to our text under here. Okay. And that should do it. There we go. Look at that. Absolutely incredible. Looks amazing. Okay. So now we've got a nice little interface happening. Okay. So the next thing we want to do is we want to speed up the progression, like the speed at which this goes across. That's basically what we want to do. But if we speed it up, we're also going to have to update our ticks as well. Update our seconds. We're basically going to have to double the length, the width between them. So we're going to have to update that in a few places. The first place is the 1 second ticks. So everything stays the same except the gap. So the gap is going to now be 12, and this gap is now going to be 120. Let's have a look at that. That should double the ticks. Yep, that worked. Definitely did work. Actually, you know what I'm going to do? I like the ticks how they were before. I like the intra ticks better how they were before. Actually, I'll change that later, but I'm going to update the text seconds. So I'm going to come back to our text, and I'm going to put this at like 11, should do it. And then instead of times that, it's going to be, instead of times 60, it's going to be times 120, because we're moving at 60 frames per second, and now we want to shift along 2 pixels per frame. So that'll be 2 times 60, 120. Let's see if that gives us what we, yep, 100%. So that gives us 1, 2, 3, 4. That looks great. Okay. So, and I'm gonna update these intra ticks. So I'm gonna double them because I think that looks a little bit better. So it's not going to be 1/10 of a second. It's going to be 1/20th of a second now, because I think that looks a little bit nicer. So go again. There we go. So the intra ticks are a little there. I've doubled the number of ticks in between, and I think that looks more aesthetic. That's more aesthetically pleasing to me. I like that a lot better. But we haven't actually increased the speed of anything yet. So the next, we're gonna update the speed of. Come down here to our draw, and inside of our draw, what we're going to do is we're going to put in a loop. We're going to update the speed of our wave first, nothing else. I'm just going to see what that looks like, which should look very interesting. Actually, so it'll be adding our window twice. That should be fine, but it will be flying past. It should be flying past a lot quicker. Okay, so let's see what that looks like. Yeah, so our top up here looks really cool. So this is going twice the speed now, and this is the speed that we actually want. So we're going to speed up the spectrogram as well to match it. So the way we do that is we put that in there, but we're going to need to grab that window as well. And we don't need our window to be printed in here anymore. That's a waste of time, but we're still going to print the number of available buffers, no matter what. Now, let's see what that looks like. It's flying by. But we've got that problem that I tried to illustrate a little while ago. We've got lots of these gaps here. See, it's missing, it's got lots of holes in the data. See, whenever we have a 0 in the number of available buffers, now we have a gap here. Now, the reason that we have this is because, as I said, we're running out of buffers and it's still scrolling along at the same speed. We don't want to change the speed in any frame, no matter what, because we want a consistent, smooth animation. Even if we have to, even if we miss, like even if we don't have a buffer available, what we're going to do now is we're going to fill in that gap with just some, whatever the previous slice was, we're going to add that, whether it's the spectrogram or whether it's the wave. And I'll show you what that looks like in a sec. Actually, first thing we're going to do, so the hop, remember our good old friend, the hop size? So if we change the hop size, remember here, this is our hop, this distance here is our hop size. So we had this just imagine we had 3 frames per second, but now we need to halve it. So we need our windows to be hopping a little bit less of a distance. And then if we do that, we won't have these gaping holes anymore. But we're going to get it really, really close, but we're still going to fill in any gaps with the method that I just talked about, where we're going to fill in, we're going to use whatever the last value was, we're going to use that. So with this, first thing we do, we're going to halve this, which will be 150 plus 35, that'll be 185. So we save that. Let's round it down. Actually, let's round it up. Let's go 188. Now, we shouldn't have that problem really at all anymore. See, it's going by. I'm trying to find when this, so this should go down. It'll take a while, actually. See, it's going down. It was 80 something, now it's 70 something. Soon it'll be 60 something. Yeah, it's taking too long. So I'm going to increase the hop size to 200. Let's go 200. Then it'll run out a lot quicker. So 80, 70, 60, 50, 40, and then soon we're going to start getting gaps. See, we've got a few. Yep, we're starting to get them now. As you can see them here. Not many of them, but we are definitely starting to get them. Okay, so you saw them there. I'm going to fix them, and this is just an aesthetically pleasing type of way of dealing with it. In the real world, if you're going to use this for something like, you know, taking audio and converting it to a spectrogram and then feeding it into a convolutional neural network sort of thing, you wouldn't necessarily you wouldn't care about like nice looking animation sort of purposes. Like you wouldn't really care about that. But for our purposes, because we are vain and we do care what it looks like. I mean, you know, we do want it to look pretty and we want it to look perfect. We don't want any of those little gaps. So we're going to go to our spectrogram, and the way we're going to do it is, so we've got this slice here, this self.slice. We're going to keep track of whatever the slice was last time. So I'm going to change this code here. This is always going to be using the actual whatever the currently saved slice is, right? But I'm going to remove this. I'm going to swap these around. So self.slice is equal to the slice. So the self.slice is going to be set to this new one, and then we're just going to use it as normal. But if the window is none, we're just going to use whatever the previous one was in the previous frame. So when we do that, we should definitely have no gaps no matter what when it starts to run out. So when this runs down, remember this is happening because our hop size is very slightly bigger than it should be. And then once we get down here, there's absolutely no gaps whatsoever. So we solve that little gappy problem, right? So it might not seem like important, but you know, this, I'm like weirdly like, you know, it's got to be right. It's got to be right. You know, it's got to be right, bro. You know, so yeah. So now we can go back and we can put our hop size back to what it was, or not what it was, but we can go back and put it to 188 is a good number. So it's just a little bit faster than it should be. That way, if we have a delay in our recorder, then it will eat into that delay, and then it will become real time eventually. Actually, we'll go 190. 190. And then we'll do it again. And there we go. So it might seem like a, you know, like an unimportant point, but as I said, I like to get it sort of as, you know, it's like a perfectionist. It's got to be right. You know what I mean? It's got to, you know, and you should be too. Like if you're a programmer, you're a serious programmer, and you're not like, it's got to be perfect, bro. What are you doing? It's got to be, you know, it's got to overtake your soul in an unhealthy way. You know, you got to love it that much. You know what I'm saying? Anywho, so we're going to do the same thing to our wave up the top, even though we can't really see the problem the same way we could with our spectrogram, but just do it anyway. And we'll do something very similar where we'll come here and we'll have a self.sample, and we'll just say that's equal to 0.002, which is really, you know, that's really small value. And then when we have one, we'll say self.sample, and then when we actually use it, we'll use whatever that self.sample is. And that should be it. That should have fixed it. Okay. It's looking absolutely gorgeous. It's looking incredible. Like I have delivered you to the promised land. Like this is incredible. Like I love looking at this. I have spent like an untold amount of time, you know, just looking at my own voice, like not my own voice, but like all sorts of sounds. I've got my girlfriend in to talk about, you know, just to hear her, like see the difference between my voice, her voice. Yeah, it's just such a mesmerizing thing to look at. I absolutely love looking at it. Like it's just great. Okay. Now that great thing we can do with our logger, so we can turn off our logger in everywhere. So we can go, in our utils, and then we can set. We only want to show errors, which we don't actually have any errors, but, and then we do that again, and then we turn off all of our logging, except we have, you know, pulse audio's, you know, annoying, you know, standard error, but yeah, that's fine. We don't really care about that. But this is it, you know, and I hope you have enjoyed the journey. You know, I hope you have learned something valuable. I hope that you have learned something valuable about programming with OpenGL and Python. You know, I hope that you know, if you like it, I want you know, comment, follow, subscribe, or you know the drill. Let me know what sort of projects you might want to see in the future, even no matter how crazy they are. If you want to see, you know, the fast Fourier transform, if you want to, you know, anything, doesn't matter how insane. You know, I like insane. I want you to, you know, this is a safe space for, you know, all of your weirdness. Okay. So I hope you enjoyed it, and I'll see you in the next one.